Yeah, now it's 10 a.m. in Germany, and I think we can start. So, hi everyone, I'm really excited to have all of you joining us today. In our webinar series, we had lots of nice talks about in silico screening and modeling, but the predicted compounds must be validated by experiments. Often we could get invaluable insights from experimental results and could better design new compounds. So I invited two of my colleagues for today's webinar for in vitro binding assays for inhibitor evaluation, Martin Hügle and Ludwig Seifert. Thanks for joining us today. And the agenda today will be, first, I will introduce our speaker, and then I will hand over to Ludwig. So Ludwig will talk about in vitro binding assays for evaluating inhibitors. And then after the talk, he will take some questions from the chat box. And then he needs to leave because he has an important phone call after the webinar. And then we will continue with Martin's talk. Martin will talk about ITC, a short introduction. And then we will also take some questions from the chat box. So first, let me introduce our wonderful speakers today. Ludwig is about to finish his PhD in the medicinal chemistry group of Professor Manfred Jung at the University of Freiburg. And he's working on assay development and screening for methylizing reader proteins. And Martin is a postdoc in the pharmaceutical bioinformatics group of Professor Stefan Günther, also at the University of Freiburg. And he's mainly working on bromodomain inhibitor development. Okay, so now I will hand over to Ludwig. And if you are ready, yeah, please, time is yours.
Thank you very much. So, welcome from my side as well. I want to share a bit of what I am doing in my time as a PhD in medicinal chemistry, which is basically evaluating inhibitors or inhibitor candidates and giving their affinity, their inhibition qualities a number. Like a KD value, an IC50 value that we can then use to compare and to optimize. In this talk, I will, of course, in the interaction between ligands and proteins or other parts of the assay or of the assay kit that are binding, I will use a bit simplified version of that to explain how the assays work. First, I will cover a few basics. I'm not too sure about your background, so I think I will cover the most important basics, and then talk about some of the assay techniques that I have been using and that I think are the most important ones. And yeah. Then I will finalize the talk with a few challenges and questions that can arise, also about the comparability of results and assay interference that is important to consider. So the first basic that I want to, a fundamental principle that I want to talk about are affinity tags. These are pairs of molecules that are known to specifically bind to each other. Maybe the most common one is the His tag, which specifically binds to nickel, and which, for example, can be used in protein purification. And these kind of, or some kind of tag is usually part of a recombinant protein, mainly for purification reasons, but this can also be utilized in assay development, these specific interactions. And yeah, that's the way I will, that's the representation I will use of affinity tags. The second fundament that I want to quickly address is absorption, fluorescence, and luminescence, which is based around electrons in molecules having different energy levels and which can be excited, for example, by light, and which can then release the energy that they gained after a short delay. So in the case of absorption, the electron is excited through the energy of a photon, and during the relaxation, the energy is dissipates as heat. In the case of fluorescence, the energy, or at least part of the energy, is released as a second photon, which has a lower energy level because of some heat that is lost in terms of energy. Of course, not really lost, but yeah, I think you know what I mean. And because of the lower energy, has a higher wavelength. So, for example, we can irradiate with a certain wavelength and get out a smaller, higher wavelength. And that's a quite efficient tool that we can use for efficient and high throughput screenings and testing. In the case of luminescence, the excitation or chemoluminescence, the excitation can happen through a chemical reaction, and then light is emitted. Now, what I also want to talk about are chemical equilibria, which is the fundament of everything that happens in these simplified versions of reality that we are working with. In assay development, we are using very simplified models. For example, we only have a solution of protein and an inhibitor candidate, maybe some kind of molecule that helps us detect this binding. But yeah, there are no more ingredients, and we can, no more ingredients that matter in this case, and we can look at the ratio of binding that is happening, which is usually expressed as the KD. So concentration of the factor of the product of the concentration of the unbound molecules, like the ligand and the protein, to the ratio, to the concentration of the bound state is expressed as the KD. So the lower the KD, the higher the fraction of ligand and of protein that is bound. And so a low KD means high affinity. That's usually what we want in drug development. So the strategy behind binding assays revolves around having some idea of a readout strategy. So for example, a fluorescent method that we can utilize, that we can leverage to enable binding assays, and building some kind of a system around that we can use. There are several assay techniques that I will cover in a bit of time, and but what I wanted to mention before that is that we can also use known ligands. For example, the research that I'm doing is focused around methyl-lysine reader proteins that specifically bind to methylated histone tails. And so we can use a version of methylated histones with a fluorophore attached as a tool, as a fluorescent probe, that's called, or as sometimes also referred to as tracer, to build assays around that. Or alternatively, there could also be an affinity tag, like a biotin or some kind of molecule attached that we can know that we can later use with a specific interaction that it offers. But this system that means as well that there is never the isolated case of just studying the binding of an inhibitor candidate to the protein, because it's already by adding this ingredient, which helps us detect the binding and the inhibition, this already means that the system that we are studying is a bit more complicated and more complex. And this already means that I cannot measure a KD value because the system is just more complex already. The experiments are usually done in multi-well plates. So this is just like 10 to 15 centimeters and multiple small reaction chambers where we can mix certain inhibitor concentrations with a combination of a protein or tracer that we need. And this is quite efficient, so it can be pipetted in like 2 to 4 hours maybe, and then measured just all at once, more or less. So this is a very efficient method. And usually all experiments are done in triplicates, which means 3 wells having the same content, and later the mean value is used for the evaluation and the analysis. Yeah, I already mentioned that the definition of the KD value, and I want to just wanted to re-emphasize that it's the most exact affinity metric, and with the highest standard, and so it's usually the KD value is specific for a certain interaction, at least at the same pH value, at the same temperature, but I'm sure Martin will tell you more about the KD value later. What I'm using in binding assays is the IC50 value, which has not as high a standard, not as much of a meaning, not the same level of comparability, but is easier to determine. So the typical result of an IC50 experiment is a serial dilution of an inhibitor is added to whatever system it takes to measure inhibition. And so a low inhibitor concentration has no effect on no inhibiting effect, and a very high inhibitor concentration completely inhibits the protein. And in between, this is the normal picture that we can see. So a logistical curve, if we look at the logarithmic scale of the inhibitor concentration. And to compare 2 inhibitors with different affinities, we take the inflection point of this inhibition curve, which is also usually also the inhibition at the 50% inhibition concentration. So in this case, it's around 500 nanomolar. The third affinity metric that is sometimes can be seen in literature is the Ki. This is usually a type of a KD value that is not measured directly, but calculated from an IC50 result. And yeah, so yeah, just that you have seen this as well. Now I want to talk about the methods that can be used in this type of efficient binding assays. The first is focused, it revolves around fluorescence polarization. So what it takes for this experiment is a fluorophore attached to a known ligand, which is excited by a linearly polarized light. So just one polarization plane. And because it's a fluorophore, it will emit a photon after a short delay, which, because it was excited by just one polarization plane, with linearly polarized light, the emitted photon usually is also linearly polarized in the same polarization plane. But because of the short delay, the short lifetime of the excited state, this fluorophore can rotate, move, and therefore it's largely depolarized, the light that can be measured from this experiment. But if this molecule, this tracer, is bound to a big protein, the mobility is largely reduced. So the fluorescence polarization in this case is higher. And you can imagine adding an inhibitor to, or an inhibitor candidate to this system would compete with the fluorescent tracer, release it again, and so the fluorescence polarization would be lower again. And so this means the fluorescence polarization tells us something about the inhibition that is taking place. The second method is based on FRET. So it's a certain energy transfer of two fluorophores that are in close proximity to one another, and it needs to the fluorescence spectra need to overlap. So we have one fluorophore, the FRET donor, that we can excite, and that will emit light in its emission spectrum. And if this emission spectrum overlaps with the excitation spectrum of the second fluorophore, which is called the FRET acceptor, this means that the energy that is released in this phase is the exact energy that is needed for this fluorophore to be excited. Then a part of the energy is transferred to the second fluorophore, and we also see some emission in its specific wavelength spectrum, although we did not excite, we did not irradiate it with its excitation wavelength. And this energy transfer is only possible if they are in close proximity to one another. So what we need for this is also a fluorescent tag on the protein, for example, like a fluorescent tracer ligand with a fluorescent tag, and there's a different fluorophore attached to the protein. The third method is that I want to present is called AlphaLISA or AlphaScreen. This is a combination of a light absorption inducing a reaction. So this is a photosensitizer. It produces singlet oxygen, so which has a higher energy level than the normal triplet oxygen, and which is quite reactive, and which can induce a reaction on the second type of bead that is used in this assay, where the singlet oxygen induces a luminescent reaction. So this is also a system where we irradiate it with a certain wavelength, and we measure the emission of light on another wavelength. But this is not fluorescence. It is because the energy is transferred as chemical energy in the form of singlet oxygen. So here I brought you an example of how this could work in practice. For example, if we want to study a his-tagged reader protein, or we want to study a reader protein, we can use a his-tagged version together with a biotinylated probe, so no ligand, because the histone, the trimethylated histone is the native ligand of this reader protein, and we use a biotinylated version of that to couple it with the two reagents that are needed to enable this energy transfer. And the maximum distance that can be covered, the maximum tolerated distance between these types of beads is 200 nanometers. which is quite big. It's much more than can be used in Fred, for example. And that means we could also use like antibodies if needed to bring these two beads together. Because yeah, sometimes it's not as easy as in this case. Leaving the biochemical assays to a biophysical assay, where we do not need a fluorescent tracer, but a solvatochromic dye. Solvatochromic means its fluorescence intensity depends on the lipophilicity of its environment. And because increasing temperature induces protein denaturation, this means that when the protein denatures, this solvatochromic fluorescent molecule can bind to lipophilic amino acid residues that are usually hidden in the inside of the protein. So because of the denaturation, the lipophilicity of the environment around this fluorophore increases, and therefore the fluorescence intensity increases. I brought you an example of how this can look. As the protein denatures, the fluorescence intensity increases, and then it decreases again because of other effects. But the important fact in this case is that adding a ligand can delay the denaturation of the protein, because there's a competing equilibrium to the denaturation, which is so a protein can either bind to a ligand or it can denature. And of course, at some point, the entropic gain of the denaturation will be stronger than the gain of free energy that the binding can bring. But with increasing concentrations of a ligand, this melting curve, as it's referred to, so which means the denaturation is delayed to higher temperatures, and we can use the change of the inflection point to higher temperatures as let's call it delta Tm, so change of the melting temperature, a Tm shift, that's also called. And yeah, this can be seen as just as an orthogonal assay method to the assays that I described earlier, because it's a completely different method. It's not built around competition, for example, as the other methods were. Now some remarks at the end of the talk. The values that are obtained with such a binding assays are only comparable if the important parameters are kept constant. So that means the concentrations of protein of the fluorescent tracer molecule or whatever is used. The protein construct has to be the exact same. Buffer and pH value should not be changed. Temperature, incubation time, and also the concentration of the most commonly used solvent for inhibitor candidates for compounds, which is dimethyl sulfoxide. Yeah, usually different DMSO concentrations have a certain effect on the assay quality. So yeah, this should also be kept constant. And if these are kept constant, the IC50 values that are obtained with a certain method are comparable to one another. Now some special cases. There are cases where the IC50 experiment does not result in such a nice curve as it is here, because sometimes when the affinity is too low, we do not see 100% inhibition, and therefore it's hard to fit such a curve. to the data that we have, and then the result is usually given as, for example, in this case, 30% inhibition at 100 micromolar. And so whoever reads it then can think to themselves, okay, then the IC50 probably should be in the range of 200, 400, or something like this micromolar. But then it's not fair to just fit a curve anyway and to say, yeah, the IC50 is clearly at 385 micromolar. So that, yeah, that's where usually also in tables in public publications, it's then not given as an IC50 value, but as this alternative representation. Another case that sometimes appears as something like this. So that could mean we are dealing with a compound that, for example, absorbs part of the light that we are using for our readout, and that interferes with what we are using. And yeah, then the best thing to do is to use a different assay method that does not rely on the same wavelength, or maybe not even on fluorescence at all. But yeah, we can then estimate in such a case that the IC50 is in the range of like 8 micromolar in this case. But yeah, this would also be a case where it's not accurate to give a where it's not reasonable to act like this is an accurate IC50. Other things that can interfere with the assay quality are bad solubility of inhibitor candidates. Absorption I mentioned already. Intrinsic fluorescence can also interfere with the emission or fluorescence readout. And reactive compounds, which can, for example, the most common thing of reactive compounds is that they react, for example, with the singlet oxygen, which drives the alpha assay, which produces false positive results. But yeah, maybe also can interfere with the protein stability. I have also in my time seen interference with affinity tags. For example, I had some false positive hits of chelators, which it turned out inhibited the interaction of nickel to the his tag and not the interaction of the reader protein to the histone peptide. So yeah, because of these specific interactions, which have a negative effect on the assay quality, it's a good idea to combine several methods, which are called orthogonal methods, because they rely on totally different readouts and yeah, different mediators, different affinity tags, different wavelengths of light, and so on. So that's what I wanted to talk about, and now I'm happy to answer some questions.
Yeah, great. Thanks, Ludwig, for the nice talk. And yeah, we used Fred assay sometimes for SHD1, but I never had any idea about AlphaLISA or yeah, the other assays. Thanks for the nice talk. And so far there's no questions, but I have two questions. So I remember in our group there was once a question asking why in some articles people avoid using IC50 to compare different inhibitors. I think you mentioned already there are many different factors that could influence the readout. Maybe can you elaborate more on this question?
Yeah, maybe I go back to that slide so
yeah,
everyone has it in mind what we are talking about. So the and in this case, what was how was it referred to the results? as a Ki value then, or?
I think IC50.
Ah, okay, they use IC50. And what is it that you were wondering about?
So there were people asking why in some journals or in some articles, people don't use or people avoid using IC50 to compare affinity of different ligands. So I think you also mentioned KD is a more exact value, but why IC50 is not reliable?
I would not say that the IC50 is not reliable, but it's very highly assay dependent. So for example, to stay on the CHD1 project, at some point I changed some, let's say many parameters of the assay protocol, because I had some optimizations that I wanted to implement, and then I did them all at once. And this led to a decrease of IC50 values by a factor of 5, I think. So a huge change. But nonetheless, before these assay optimizations, we already had comparable results. We only would have lost comparability if I changed these assay parameters and acted like it's comparable to the values that I had obtained before. So with the new assay protocol, I retested the old compounds, and then they were comparable again. But for example, if we have an inhibitor with like an IC50 value of 1 micromolar, it's quite possible that with a different assay, or it's probably even that with a different method, we would have an IC50 of maybe 500 nanomolar, maybe 3 micromolar, and so on. There's a certain range that the IC50, and another thing to keep in mind, the IC50 is usually above the KD value, which has 2 major drivers. For one effect is that there is always a certain concentration of the protein that has to be bound to in order to get a 50% inhibition effect. Because it's possible that we have a KD value of like 1 nanomolar, but we have to add 50 nanomolar inhibitor to bind to half of the 100 nanomolar protein level that we have that we are using in an assay. For example, this is one driver of why IC50 values are higher. The other factor is that the fluorescent probe, or whatever is used in this case, that has to be competed with, and this is also a driver of why the IC50 values are always above the KD values, which I think this mathematical model represents quite nicely.
Yeah, thanks. Great. So if I summarize the content of what you said, which means if it's inside one working group, if they use the same assay conditions, then the result is comparable. So you can see the trend of the affinity increase or decrease. But but among different groups, when they use different assay conditions, then the absolute value of IC50 cannot be compared with each other. So let's say.
Not if they are using a different assay protocol. I think assays are reproducible enough to do it with the same procedure in a different group, in a different city with a different reading device. This should be possible to compare, but not with different assay setups. Yeah,
great, thanks. Now we have another 2 questions in the chat box. So the first one is, does high binding affinity indicate a potent activity in vivo? You know the solvent environment can affect the binding affinity of ligand. How about it in human body?
Yeah, I agree that it's a very simplified view of what we want to achieve, which is of course a potent activity in vivo and in the human body. The thing is yeah, and I am aware that this is an oversimplified model of the reality, but the fact that this is as simplified as it is allows us to have high quality data that we compare to one another. If we start all experiments in cells, for example, this already would be a simplified version of the in vivo state that we want to reach. But we would lose a lot of efficiency, a lot of accuracy because of competing effects that we cannot know and quantify at that point. So how this procedure works is usually we start with these kinds of binding assays. So a very, very simple version of just a recombinant protein solution and an inhibitor candidate, and maybe some tools to help evaluate the binding. And then next we can do experiments in cells with the best candidates, and then we can move on to at the end experiments with humans. But so to answer it in a shorter way, it does the high binding affinity does not mean potent activity in vivo, but it's the best predictor that we have at that point.
Okay, yeah, great, thank you. And the next question is Ki and Kd represent the same meaning? Are the values same? I think you also mentioned, so here on this slide, Ki is a Kd calculated from the IC50.
Yeah, in a perfect world, it's the same. That's how I would phrase it. But yeah, usually this is used in a way where this is a Kd value that is not measured directly, for example, with ITC, but in an indirect way where it inhibits another competing binding. So this is naturally less accurate. But yeah, in theory, they should be the same value. Yes.
Yeah, thanks.
But it's very easy for systematical and random errors to distort this, the Ki compared to the Kd.
Mm-hmm. So basically, so Ki is calculated from IC50, which means all those factors which influence the IC50 could influence Ki value also, because it's calculated from IC50, which means all those factors which could affect the accuracy can also goes to a Ki value, right?
Not all of them. The most important ones, the two drivers that increase the IC50 values that I just talked about, which is the protein concentration and the Kd, or the concentration of the competing fluorescent probe, they are in theory eliminated in the calculation of the Ki value. But I'm not very convinced of the accuracy of this calculation step, because there are, for my taste, too many assumptions that have to be made. For example, how sure am I of the Kd value of this interaction? How well did I measure the concentration of the tracer? How stable is it even? And so that makes it a bit difficult. And also, if you imagine the case of a Kd of 1 nanomolar inhibitor with 100 nanomolar protein concentration, which does not go that well together. If you imagine you have an IC50 of around 50 nanomolar, and you know this is the minimal IC50 that you can measure, do you really know if it's a 20 nanomolar Kd value of the inhibitor or a 1 nanomolar Kd of the inhibitor? or even lower than that, because they all will result in more or less the same IC50 value, which is the assay limit at that point.
Yeah, okay, great, thanks. I have a last question. So you said if we use the same assay protocol, assay condition, the same machine, then basically in theory we should get the same IC50. And now I had just the question, if different people, they use the same protocol, the same machine, is it possible that they still get a different IC50? Like the way how you do the experiment, how much does that influence the readout?
You mean also using the same starting solutions and so on, the same stock solutions?
Yeah, because I remember when I was doing master here, I remember we tried AlphaLISA. I remember there are many steps where you need to add the beads and then you need to add some solution and then wash. And so I think the way how you do the experiment can also influence the readout. Like maybe
I think alpha is the best example for this. In all cases, it would require a certain pipetting reproducibility, and I mean pipetting mistakes can happen, and there can also be systematical differences, small systematical differences of different people pipetting the same steps. But alpha is a very special case because it's also susceptible to light, so it should be pipetted quite fast and not as dark as possible in the room and so on, which makes it a bit it's one of the more challenging assays to pipette, and I can see that the results will vary more in the alpha context.
Okay, yeah, thank you very much. Now we don't have any questions in the chat box, and I think now we can finish this part. And thank you again, Ludwig, for the nice talk and for the questions. And I hope your interview is going well later. Yeah.
Yeah, thank you.
Okay, thanks again. Okay.
Bye. Thank you for the invitation.
Thank you. Yeah. So now we can continue with Martin's talk. Now Martin will give a talk about ITC, a short introduction about ITC. So yeah, now I can see your screen, Martin, and if you're ready, you can start.
So welcome to my talk about ITC. And I will start with a short introduction to the experiment. And here, first of all, the most important question is what can be measured by ITC. Here we have all the thermodynamic parameters, delta S, delta H, delta G, which we can determine by this experiment. And the only thing that is needed, therefore, is we need to have a detectable delta H, because this is what we, in the end, measure with each injection. So how do we do it? Here we have our ITC cell. And this ITC cell, we have we have one reference cell and one sample cell, and we usually measure the power that is needed to keep both cells at the same temperature compared to a reference power. And then when you have an exothermal reaction taking place in the sample cell, like most of the bindings, and then you need less energy to keep both cells at the same temperature. So you will see something like here. And then you see most of the time that we have here a first injection, which is a waste injection. This we are doing because of our syringe. So this is a typical ITC syringe, and it's just open at its end. And here in this tip region, then during the calibration, you have some mixing already with the binding partner in the sample cell. So To measure only stuff that is not already bound, you do at first a waste injection where you get rid of it, and then you have just pure binding partner from the syringe. So now that we have our raw thermogram, I usually use the program Nitpick, which I can highly recommend, to find the baseline and to integrate the spikes. And here this program does something special. It analyzes the noise of your curve or of your baseline, and then it simulates for the whole thing a noise on top of the spikes. Then it reconstructs the whole thermogram and integrates it. And then you will end up with an isotherm, which you can see here. And then we need to go to a next program and do a model selection and a fit. Here I usually use this ITC SY. It is also like Nitpick, a freely available tool, which I use usually. And here you have then quite a large selection on different binding types. And with this different binding types, different shapes of our isotherms are usually coming. So in drug design, we have most of the time sigmoidal curves like here in the first case, and this is usually just an A+B binding. And yeah, it can become much more complicated when you have different binding modes, and also then your isotherms and thermograms look quite different to what we usually see with drug design. So as this becomes much more complicated, and most likely you will not get directly reliable results from one measurement, I will just talk today about this most simple variant here, where you have a sigmoidal curve. So what can we extract from our fitted data? First of all, we can extract delta H, which is given by the height between the first and the second plateau. Then we have the affinity, which is given by the inflection, the slope in the inflection point. Then this is also delta G, given by this well-known formula here. And as you directly can see here, you can then calculate delta S. This you should keep in mind. Delta S is calculated and not directly measured from your experiment. So this curve here is, however, a rather optimal case, and more often you see different types of this sigmoidal curve. And yeah, here we have a so-called C factor, which we can use to describe the shape of our curve. And here the C factor is given by the binding sites of the compound in your cell multiplied with Ka or divided by Kd, and the cell concentration. And this value should be, according to this publication, around 20 to 100. And this would mean here between this blue and this purple curve here, I personally would say still with a C of 5, you can have nice reliable data. However, you need to consider that you have different arrows for different C values. So for high C values, you have a well-defined plateau region in the beginning and in the end. And then you can measure with high accuracy the difference between these two plateaus. And For KD, it is quite the opposite, because you need data points under your inflection point and under this part here. So when you have a step-like increase here, it is highly unlikely that you have several data points on it. So you like more to have something where you have more data points under it, so to get the most precise slope in the inflection point. In the end, you can also think about delta S errors. And here again, it depends on delta H and KD. Therefore, you have two options. First option is to use a balanced C value to get then also a meaningful delta S. Or what you also can do is you do one measurement with a high C and one with a lower C, where you then in the end combine. But keep in mind, at very low C levels, like 1 and below, you will not see anything anymore. So it will also result in a bad KD estimation. So now let's have a look on the real thing. So here I have selected some of my old measurements where I show 1D arrow surface projections. This is probability on the y-axis plotted against KD and delta H on the x-axis. And as you can see, you have here for a nice sigmoidal curve, you have here a narrow region which gives a high probability for the fit. So for something like this, you have well-defined results. When you now have something like here, where you can directly see you have very low C value, maybe you ask yourself, why don't you increase concentrations? In this case, I can tell you it's not so easily possible, because you are already in a very high KD range. So you need to go further up with your concentrations, and then you will at some point come to the problem that either your ligand is not soluble anymore, or your protein cannot be concentrated anymore, and then you just can measure at a lower C level C value, and then you will end up with something like here, where you have usually for the KD an acceptable, still acceptable value and probability. But for delta H, you can directly see this curve doesn't give you the real thing about delta H. And then you will end up with a low probability. And in the worst case, when you have even some noise, then you will end up by with something like here, where you do not have a defined lower value at all. So you just can say we have a value that is worse than something. However, it still is enough to say, for example, we have here a very nice binder with a very good KD, and here we have some more molecules that are not so well binding. But keep in mind, these values are not highly precise, and they represent, like here, only an upper limit, but not a lower. So then let's come to some problems with ITC. And here we have, for example, the so-called spacing. Spacing is the time that you give the reaction or the binding event to go back from the interaction to your baseline. And In this case here, you have a second reaction coming up over time that takes longer. So you have at some point less and less baseline, which you will need to calculate and integrate your data. And already here, it becomes quite hard to see a baseline anymore. And at some point, you start even with the next injection prior to really getting back to your baseline. And that means that you have in the end something like this here, where yeah, you can directly see it's not a nice baseline, and you will end up with some more or less useless data. The solution to this problem is just to increase the spacing. However, keep in mind you cannot increase spacing unlimited. For example, sometimes protein stability get a problem. When you see here, you have here quite some time that passes during a normal measurement. If you now increase the spacing a lot, it will take much longer, and maybe your protein is not stable enough to for a very long measurement. So there come also new problems maybe. So about the C factor, we have talked now a lot. So I think it's clear here. You just have to change the concentrations, and then we have the so-called reference power. The reference power is the power that you give to your reference cell, and then you measure the differential power. This reference power is more or less your baseline power, and you need to keep this as high as necessary, but as low as possible. This means when you go up with this reference power, you will get more and more noise. So keep it low, but don't keep it too low, because you should never ever touch the 0 line with your spikes here. So you need to keep it balanced. And then sometimes you have some more or less strange looking curve like this here. We have in the beginning some hook-shaped start, and this can come from a too long calibration time when you have a lot of mixing inside the syringe before you do your first injection. So to check on that, you can increase the first injection volume, this waste injection. However, if you have something like here, it would mean that you have already 3 injections, full injections, that you need to replace, because it would have, it should go here not down but up. So it's not likely that it is, in this case here, a problem with mixing inside the syringe, and but you can already test it, and yeah, sometimes it is just a problem with too large calibration time in the beginning. So the second thing that comes in mind is to do a reference measurement. This is especially important when you have a drift in your baseline or a slope, like you can see here. So this should go basically to a flat line at some point. But you can see here you have some upgoing still in, and this can be a dilution effect of your binding partner in the syringe. So you're diluting your binding partner with each injection. So you have a high concentration in the syringe, and then you inject it to the cell, and thereby it gets diluted, and it can end up in some drift in the baseline. To get rid of something like this, you're doing just a reference measurement where you usually inject your binding partner into buffer in the cell. And then you subtract the data from this reference measurement from your real measurement. And sometimes something like here with a slope in the end will end up with a perfectly flat plateau. However, in this case here, with this strange shape at the beginning and the slope in the end, it's more likely that you have a different binding model, and then you need to change your binding model. However, the most common problem is the molar ratio at inflection point. So you will see a lot of times something like this here, or maybe that the inflection point is somewhere here, but not at 1. And here you can think about maybe of the wrong model, but usually it is A plus B binding, and the thing that is wrong is your concentration, because your concentration is much more likely to have some failure than that you have a second binding, or maybe something like a 0.7 binding, or here it would be somewhere around 1.6 maybe. So you would have a molar ratio of your binding partners of 1.6. This doesn't make much sense. So the question then is, which concentration do we trust? And the sad answer to this is we can't trust any concentration, because we have for the protein concentration and systematic error. That means the values are quite close together, but we do not know the real value. So we have a systematic error of the protein concentration, especially within one batch, where you maybe during the purification do one concentration measurement, and then you take this as a given concentration for all the following up measurements. With ligands, you usually have more of a random error, especially when you buy your ligands from different suppliers, or you get them from different cooperation partners. So then the next question would be which one to use to keep as a reliable concentration. And here I usually use my protein concentration because of its systematic error with a high precision. That means it is perfectly fine for an internal ranking, but we have a problem to compare with others. And here I usually use then a comparison measurement where I buy an already published compound, if there is any, of course, and then I measure it with my method, and then everyone can easily compare my results compared to already published results. However, keep in mind that temperature is a really important factor for ITC. So usually at lower temperatures, you will end up with higher affinity. So always have a look on the temperature that people used for their ITC experiments. And you will find it sometimes hard to find this temperature, because sometimes people do not mention the temperature that they measured. And in the end, I like to sum up some pros and cons of this method. So we have a label-free method. This means we just use a buffer and usually a protein and a ligand for the protein. We do not have any of this probes or fluorescence dyes or whatever. So this means label-free and it's quite accurate. Then we can determine all the thermodynamic parameters, and for drug design it's highly interesting because you can then optimize your ligand in terms of delta H or delta S, and you can directly maybe see some influence of some parts of your ligand. And within one batch of protein, we have a really high precision for our data. On the other side, ITC is really not for high throughput screening, and there is mainly one reason. So you have an enormous protein consumption with each ITC experiment. And when you remember what Ludwig said about his experiment, some 100 measurements within some hours, for ITC, you will usually use something like 2 hours per one measurement. So then we have this problem with poor comparability, and not always you will find a ligand that you can buy to compare with your method. Yeah, and then you also have often a problem that interpretations of ITC data are not quite correct. And also that we do not have access most of the time to the raw data, so we cannot recalculate our own, but have to trust the published data. So with this, I'd like to thank you for your attention, and are there any questions?
Yeah, great. Thank you, Martin, for the nice talk. Yeah, we have some questions in the chat. The first one is, for multiple binding site protein, how can we choose model based on the curve shape or something else?
One second. Yeah, it's a bit complicated. So first of all, you have to check which kind of binding model you have. For example, here you see this A plus B binding. You have two different binding modes. So symmetric sites means you have an A plus, or you have one binding partner that can bind two other binding partners in the same way. This is usually not the case because you have, maybe you have two symmetric sites, but this doesn't mean that they bind exactly the same. And most of the time you have one side that then influences the binding of the second side, even if it is 2 times the exact samely binding side. But already statistically you have a change. So usually this here with 2 symmetric sides can be used when there are only little differences. And otherwise, you need to use this with non-symmetric sites for such a case. And unfortunately, you cannot tell by shape directly which model to choose. Sometimes, for example, you see something like this, where you have a first binding and then a second binding event. But also the curve that I showed later on this one here is most likely something like an A+B+B binding. And yeah, it's very hard to tell from the pure shape which binding mode you will have. So this is something you need to think about what makes most sense. So it's highly unlikely that you have a second binding site somewhere on top of the surface that binds with a similar affinity and so on. So there you have to take a lot of things into consideration.
Yeah, great, thanks. The next question is a nice talk about ITC technique for determining the binding affinity as golden standard between two molecules or more, but can be used to detect the enzyme activity? Do you have any experience or suggestions?
It can be used for this. There are some really nice papers. However, I would not recommend it. So if you have any chance to do it with another method, it will be usually faster and less protein consuming, because you can't do this with one measurement, but with a series of measurements. And you really need a lot of protein for one measurement. So you most likely do not want to do something like 3 or 5 measurements to get then and somehow reliable, for example, Michaelis-Menten constant.
Yeah, thanks. Okay, I have also a question. So regarding our own project, I remember Holger always showed the N value on the plot, and that's the molar ratio of the ligand and protein, right?
Yes.
Okay.
Yes, exactly. So here, this N is the molar ratio at inflection point, and especially with older software, the people use then to give this N value. So I personally do not do this. I personally say my protein concentration is my assumed to be correct concentration. And then I just recalculate the cell concentration. So usually I titrate protein from the syringe into the cell where I have then a ligand. And then I just tell this ITC-SY program that it should fit the concentration of the cell. So then you will end up with then you will end up with a molar ratio at inflection point of exactly 1, because it will just shift the shape, shift the molar ratio or the concentration, and yeah, then you will have in this old method an K of 1 or an inflection point at exact 1-to-1 binding. I know this is not 100% correct, because you always have some errors in concentrations even within the same batch of protein, like a pipetting failure or something like this. However, for an internal ranking, it makes much more sense to use it to do it like this. And yeah, if you think about binding mode and stuff like this, it's highly unlikely that you have something like my protein binds 1.7 molecules. This just doesn't make much sense.
Yeah, thanks. So maybe another question about the binding model, because I don't see quite often in publications like the curves with 2 binding, because I think most curves that I see is just one slope, one inflection point.
Yeah.
Does that mean that actually most of the ligand, they bind just with the 1 molar ratio, 1 ligand bind to 1 protein? And how often do you see 2 ligand binding to 1 protein?
So of course, when you have a protein with 2 binding sites, you will have 2 binding events. But usually in drug design, we have most of the time this A plus B binding and no other binding. When you think that you have a highly designed and specialized binder for your protein, and then you think you have something, so for example, when you have something like this here, when you have a second binding event, to see it in such a curve, it has to be at a comparable level at least. So maybe 1% of the strength of the main binding you could see still, but a very, compared to the main binding, very weak second binding, you will just not see. Of course, you have most likely for each protein some binding on the surface, but it's too weak to see it in your data. Only when you have some second binding that shows comparable strength, you will end up with a clearly identifiable second binding. So most of the time you will end up with something like this, unless you have a second binding site which can bind in the same range. And this is just usually not the case, especially when you have a molecule that has just 1 binding site. Then where should your second molecule bind with a comparable affinity? It's just highly unlikely.
Yeah, great, thank you. I have a last question. I think it's a more general question because yeah, we learned a lot about the pros and cons and all these details, how to interpret data. And I think most of my audience, they are doing more computational modeling and simulation. And oftentimes we just maybe like me get the plots already fitted from the collaborators. And do you have some suggestions on how to check the data, how to interpret the data, or how to find maybe something is wrong in the plot, just to do not like manipulated by the curve fitting and get more insights from the plot for new design? Like what's the most important thing that when we check the plot?
It depends on what you like to see, like I showed on this slide. For some people, delta H is most important. Then even measuring at the extremely high C value would be okay. Most of the time you are more interested in a KD value, so a lower C value would be okay. However, I personally think when you're doing already ITC, you should use its full potential and not only measure a KD. The KD, of course, is that what you most often see and most people will use. However, when you like to design your ligand, sometimes you can see you're doing one little change and you have a trust on the ligand, and you will have a drastical change in delta H or delta S. This is then something that you can optimize for. And then you should, of course, measure with the needed precision to get reliable data. So keep the C value in the mid-range for something like this.
Yeah, great, thank you. Yeah, maybe one last, very last question. You mentioned that people don't publish the raw data of ITC experiments.
Unfortunately, yes.
Yeah, and why not put it in the supplementary material?
I'm not sure why people don't do it. I personally have also not done it in the past. What I usually do is I add, in the past I added some plots like here, or what I nowadays do, I give boundaries for this probability level. So I calculate probability level at 99%, and then people can see how broad the range is in which the values are. So this gives you some idea about the reliability of the data. But you're right. We should, of course, publish somewhere the raw data as well.
Yeah, great, thanks. Sorry, I have one last question. So
no problem.
Yeah, so on this slide you have the delta G, delta H, delta S. So delta H is a value that we can directly read out, and KD also can get from the inflation point. And then you get the delta G from the formula and delta S from the delta G formula. So if in our case you see two compounds, yeah, quite similar, but you modified one functional group, and then you see a dramatic delta H or delta S change, and how are you going to interpret the data and use that for compound design?
Interesting question. So yeah, it depends. Of course, when you have so usually most of the binders are delta H driven binders, and delta S is less important for most of the bindings. However, when you see something like you're doing some little adding of a group, and delta S is then getting largely positive and so on, then you can use this data to in combination with structural data, especially, you can use it then to think about why is it like it is. So for example, when delta S gets positive, you usually have something like replacing and tightly bound water in the binding pocket, and then delta S will be positive because there are more available states in the end than in the beginning, because you have more chaos. Delta S gets positive, and then you can optimize even for something like this. And the same is true for delta H. This is also what most people like to focus on. Delta H interactions are, for example, the hydrophobic interactions mainly, and you can then with this data and in combination usually with structural data or with a good model, you can then think about even increasing this effect, and this then can give you some clues how to further develop your ligand.
Yeah, great, thank you. So if I understood correctly, you mean if we have a positive delta S change, very likely we replaced a water molecule in the binding site, because when the water molecule gets into the bulk solvent from the binding site, then the entropy increased, or it's entropy driven?
Yes,
okay.
But you can have also other cases, like you have maybe there's binding in lysine, and in your binding pocket, and when you now bind your ligand, then this lysine gets free and it becomes from a highly ordered state to a highly chaotic state, and thereby delta S will also increase. So it doesn't have to be necessarily a water. It can be also a cofactor that you replace, or it can be some chains in the backbone or whatever.
Yeah, thank you. So we have a new question in the chat. Maybe let's just have a look at the last question. When you just now talked about N value, I saw some references indicating that if N equals 1 but 2 at saturation, then your one molecule in cell can bind to one molecule from syringe injection 1-to-1 ratio, correct? I'm confused from one of my reviews. He said should be 2-to-1. I'm not sure if I understood the question correctly.
Yeah, I'm also not sure if I have understood your question now correctly, but if you show something like this, then the referee will maybe tell you, so your binding is not, or your molar ratio is not correct, because 1.5 doesn't make much sense. So what you can do with the programs I showed you in the beginning is you can recalculate or fit the concentration of one of the compounds, and thereby you shift the molar ratio exactly to the inflection point. This should be done carefully, so keep in mind, are there possibilities that you bind more than one molecule, and then think about this. Are there any reasons why your protein should bind two molecules with exactly the same affinity? Otherwise, it is most likely a problem with concentrations, and you should adjust the concentration of one of your binding partner.
Yeah, thanks, Martin. I hope we answered the question. Okay, yeah, yes, we answered the question. Yeah, okay, great. So thanks again. And I think I, during the talk, read one word in the wrong way. It's inflection point. I said inflation point, so sorry about that. And now we don't have any questions anymore in the chat box. And thanks, Martin, again. Thank you very much for the very detailed talk about ITC, and I think it's really, really helpful for a drug designer to interpret the ITC plots in the correct way. Yeah. Or,
you're welcome.
Yeah, and also see some problems maybe from the plots. Okay.
Yeah.
Yeah. Okay, thank you very much again, and thank you everyone for joining us, and hopefully we will see each other next week. This Sunday we don't have any webinar. Yeah, because our webinar is now on Thursday. Okay, yeah, then have a nice day and nice evening and nice weekend. Bye-bye. See you next time.